Okay, welcome everyone to the March 2023 meeting of the Memphis Astronomical Society. I'm your host, Jeremy Zeldin, and president of the Memphis Astronomical Society. I want to welcome everyone. Happy spring, almost. Got another great program for you guys tonight. Very informative presentation by one of the rising stars at the University of Memphis. So we'll get to that in just a second. He's going to be telling us about the history of the universe from the Big Bang to beer. So stay tuned. But before we get started, again, just a few preliminaries. We're the Memphis Astronomical Society. We are a non-profit public service organization promoting interest in education in astronomy and related sciences. To learn more about us, you can go to the website memphisastro.org. And if you want to be added to our list, if you're not on our email list already, you can either go to our website or just click or go to the other website is joinmas.com, and then you can just be added to our email list. We send email notices out about once a week. We're also on Facebook, and of course we're on YouTube, so I want to say hello to our YouTube audience as well. If you haven't already, please take a minute to subscribe to this channel. Hope you get some great information out of tonight's meeting again. Again, our website is memphisastro.org. If you are not on our email list already, all you got to do is click the join button. It'll bring up a separate form. You just fill out your details. And again, that's how we stay in touch with you. That's the best way to learn about upcoming meetings, events, anything around town. So anyway, that's more about us. memphisastro.org. Now, for outreach requests, we do this as well. We have a form on our website. Just click in the contact, schedule talk, and or telescopes. And again, a detailed form comes up. Give us as much information as you can. We have an outreach team that services requests pretty regularly. So we do events for schools, for libraries, for special interest groups, just anything, when of course we're clear. So, but yeah, whether it's a presentation or you want us to come out and bring our telescopes, just fill out that form, and that's the best way to engage with us if you're interested in outreach services from the Memphis Astronomical Society. Okay, upcoming calendar of events. Happy March. Tomorrow is my 27th birthday.
Again?
That's my story, and I stick to it. So, some of you may have got birthday cake earlier. 27 is what happens as you get older. Going with the Alfred Hitchcock look. Get a little bit more girth here. Going from Venus to Jupiter as you get older. We've got an active month coming up, weather pending. So I just want to take a minute here to let you know what we got coming up. Monday, this coming Monday, March the 6th, we're going to be at Senatobia Elementary. In fact, our group is right over there. Everybody say hello. Hey. Group from Senatobia Elementary. This again is part of the STEAM outreach. STEAM is science, technology, engineering, art, and math. Is that right?
Yes.
It used to be STEM, but now that gets confused with stem cell research, which is controversial. So they added the A in there to get the art for STEAM. So STEAM is more politically correct than STEM. So anyway, that event is going to be Monday in Senatobia, Mississippi. So if you are available, you can bring your telescope out for that, weather pending. We got that coming up. Following night, March the 7th, we have an event for the Scouts in Bartlett. So we'll send a notice out about that. Our next dark sky observing session is scheduled for March the 18th. And again, we do these once or twice a month around the time of the full moon. March is typically Messier Marathon month. If you want to, go about trying to knock out all 110 Messier objects in one night. And in fact, for those of you who want to stick around, we got a new prototype of a Messier Marathon booklet that we just put together. This is kind of the beta rev. So if you want to take a look at this and see what it is, we're tweaking it. But very informative. This is how you learn the night sky. The Messier catalog. It's got charts, it's got pictures, and kind of detailed instructions on how to find them. This is how you become a competent amateur astronomer. You can find all 110. Not only do it once, but do it twice. Or if you're a glutton, you can do all 110 in one night. It's like a hot dog eating contest. And March is typically the best month for that. So check it out. And if you want to give us feedback, again, we're kind of tweaking it, trying to make it better, but we'll have it up here at the end of the meeting if you want to check that out. So that's March 18. Now, the following Friday, March 24, we got a lot going on that night. We're going to be at Bobby Lanier Farm Park. Again, it's right in Germantown, very convenient location, typically for a lot of people. Usually a great turnout. So if you're looking for something in town, we typically have a lot of telescopes that come out. And again, if the skies are clear. So that's a good event to circle on your calendar. And we've got another event coming up that evening, but I'm going to save that until just a little bit later in the presentation because I want to have somebody else talk more about that. But March 24 is, in terms of observing, we're going to be at Bobby Lanier Farm Park. The following night, the 25th, we've got Camp Courier in Hernando. I believe that's been confirmed. And same night also, March the 25th, we've got an event at Pinson Mounds Archaeological State Park. It's about an hour's drive from Memphis, Pinson, Tennessee, not too far from Jackson. Pretty impressive location. You get these gigantic mounds, wide open spaces, and they have a visitor center there with a lot of interesting artifacts. So if you're looking to get out that evening, again, pending clear skies, that's March the 25th. We are confirmed for that evening. Is that correct? We are. All right. And again, we'll send email notices out about these events as well. Right, daylight savings starts March the 12th. Next Sunday, we spring forward. So it gets it'll be light till 8 o'clock, right? Daylight savings, the bane of all astronomers. So the following Friday, as we end the month, we got 2 more events planned. March the 31st, we got one at Botanic Gardens, and then also the Lichterman Nature Center.
Oh, it's been canceled.
Oh, Lichterman's been canceled? Okay. So I'll take that off the calendar. Oh, we're still on for Botanic, correct? All right. So Botanic is on, Lichterman is off, March the 31st. And again, that's in town. So again, if you're on our email list, we'll send email notices out. All this stuff is weather pending, so we hope for clear skies. And we usually make a go, no-go call that morning. So skies are clear, we notify you, come out. Otherwise, if we have to cancel for weather, we notify you as well. So another reason to be on our list. But anyway, that's what we've got coming up. And again, you can always go to memphisastro.org, click the calendar link, and see what we've got scheduled for when we get the month. All right, take a moment to acknowledge some new members. Whether you're in the room or on Zoom or not here at all, I won't point anybody out, but I just want to say the name. Rick Smith, approved February 4. Welcome to the Memphis Astronomical Society. And Robert Latta. Ross Coleman, welcome. Jen G, approved February 5, welcome. And Jim Greer, welcome to the Memphis Astronomical. Hey, there he is. Somebody showed up. We have a long-standing tradition of announcing names when the people don't come to the meeting, but we figure the more names we announce, the higher the probability that somebody will be here. Welcome, Jim. Nice to have you aboard. And of course, if you're a member, you get access to the meteorite. Check out this month's edition. We've got some good information in there. And a presidential rant about how we need to document more, just saying. But anyway. Also, Slack is a good way to engage with us. This is kind of a, blog, more of a platform where you can chat. Is that right? Okay, chat. Where people share information. This is where you get your questions answered, share ideas, and just kind of get more niche focused on what we do here in the community. So if you're a paying member, we'll send the updated link out this month to our list. The link is good for 30 days. So if you're not already, think about getting involved in Slack. Good way to get your questions answered and engage with us further. All right, I mentioned this last month. We did have a comet, not quite as impressive as NEOWISE or Leonard, but still pretty good. And I threw out kind of a challenge to try and grab a couple pictures of this as it got close to Mars, as well as NGC 1647, the Pirate Moon Cluster. So I just want to show a couple of these. This picture was taken by James Holland near Randolph, Mississippi, and these are on our Facebook group. You can see here the green comet, got a little bit of the hue there, and Mars is blocked out by part of the the zoom, but it's in the same field of view, as well as the red giant star Aldebaran. Very nice shot. And this one was taken by John Holderman, and also a very impressive shot. You can see the cluster there, you can see the green comet there, and Mars right up here on the edge. And he actually labeled them as well. So another pretty cool shot. Anytime a comet comes in close proximity to another object, it's kind of a neat photo op. And how many of you saw this? Anybody? We had a couple of clear nights earlier this week. Not a bad iPhone opportunity for those of us who are maybe just getting started in astrophotography. 2 planets for the price of 1. Always neat.
Is that your house there?
No, this is the bingo house. So across from my subdivision is a retirement community. And you have to be 55 years of age. And you have a gated community with a bingo house. And what really scares me is in a few years, I will be eligible to spin that community. I did not really. Father time creeps up on you quickly. I don't know how it happens. But right now I live across the street with all the young people. And there will come a day when I may want to consider this. So, I don't know, maybe this is a little foreshadowing. Who knows? Anyway, I got a nice view of the western sky here, so yeah, nice shot. Okay, speaking of astrophotography, we do have a focus group if you're interested in getting involved and learning more about this fascinating hobby. It meets once a month. Our next meeting is next week, March the 8th. We also have a form on our website that you can fill out if you want to just kind of introduce yourself and enter some comments about things that you want to learn more about or anything you're kind of working on, just to kind of get involved. It's kind of like a moving train. You just kind of jump on whatever you want to and then just sort of participate and learn as you go. And our past meetings are on our YouTube channel, so you can always go there and kind of brush up before you join. And they've been working on a project, an image processing project for the Astro Imaging channel. And one of our members, Kanwar, represented us, or represented the MAS community for the Astro Imaging channel. So that's kind of cool. So you can check that out. In fact, I'll put a link to that particular presentation in the comments below this YouTube this video once it goes live on YouTube. So, and yes.
Can I add, the primary function of this group is to get learners and teachers together.
Right.
We have some very good experts in astrophotography and image processing that are members of this and love to share what they know. So at any level, from cell phone astrophotography to dedicated observatories and equipment, it's all there. Come pick up what you can, and if you've got to share that with the others who are trying to learn. That's the whole concept of this group.
Right. Match up learners and teachers. How to get the mentoring and the teaching as you go. So, but this group is evolving. We started it, about a year and a half ago. So, in fact, I've got an exciting announcement tonight. We can officially unveil a new logo specifically for this group. The MAS, or the Memphis Astrophotography Focus Group, is no more. We are now officially rebranding it to Mass Fits. And of course, Fits is the name of the file if you're doing this, doing the image processing. And here's the logo here with the Orion Nebula in the background. So we are now the Mass Fits.
In case you've missed it, it's kind of like Misfits, Mass
Misfits, Mass Fits. And we got t-shirts and wall caps coming soon. And we need to trademark this. So that's our next project. So anyway, pretty cool. If you want to get involved in astrophotography, this is a good group. March 8th, next meeting. Okay, last thing. We've got an exciting project coming up, and I'm going to ask Joanne to come up and tell you more about it. But the University of Memphis is one of a handful of sites in the country that has recently acquired a scale model of the solar system. So you see models of the solar system with the planets and the sun, and it's nice, but they're typically not to scale with how far apart they are in space. And this has recently been installed. This is me a couple of months ago. Well, actually, I think it was January, the last time I was there. You can see it was actually in a crate. But Joanne pinged me this morning, or earlier today, and just informed me it's up and it's ready to go. And they're officially having a grand opening later this month. Now, the Memphis Astronomical Society is a donor for this project. In fact, a major donor. And I can say that right now because Merrill is not here, and he's our new treasurer, and he is kind of a tyrant. So Merrill, we're going to block this part out. So, but anyway, this is an exciting project. We got a grand opening coming up. And Joanne, I'm going to ask you to come up and just kind of tell people more about what this is and what's coming up. You can give me my microphone. So our Zoom audience can get this as well.
Oh, and you've got the flyer up there.
I did, but I didn't get the stuff that was on your iPhone, so do the best I can.
Oh, okay, well, Dr. Jeff Bennett wrote the astronomy book that I've been teaching from for over a decade, and I didn't even realize that he's the one that came up with this scale model of the solar system. It's in his book, but I didn't know that he came up with it in the mid-'80s. And he is going to be here for our grand opening on March 24th. This is actually the VIP tour on the 23rd that I sent to Jeremy because the MAS is a major donor, and your name is in a list of the major donors on the entrance storyboard at both ends. Okay, it's 2,000 feet long, and it stretches from the north end of campus by the art gallery and gets almost to the railroad tracks, if you're familiar with our campus at all. And this is going to start at the sun at 4:30, and then he will give a tour, and by the time we get to Neptune, we'll be at the reception area. So a little reception. And then the next day is the grand opening at 1, and the president of the university will say a few words, and Dr. Bennett will say a few words, and so on and so forth, and then people will just get to see the results. You can go anytime, okay? It's not. You can go see it anytime. But Dr. Bennett will just be here Thursday, Friday, and Saturday. Then that evening, some of you may have been to our annual endowed lecture of physics. It's the Lois McLaughlin Donaldson endowed lecture of physics. Guess who the speaker is? Dr. Bennett. And this topic is pathway to a post-global warming future. So it's upbeat. Sounds like that. And then on Saturday, 25th, he says he likes to keep busy. At 10 a.m., he's going to give a talk at the Rose Theater about how to teach earth science in the universe using the Memphis Voyager system. Okay. So that's it. Thank you.
So that's the 23rd, March the 23rd, and then the lecture's on the 24th, correct?
Chairman, if I Google that, is that website online?
That is...
I just got that flyer today. Right. So if you go to the physics department website, I think there's something on it, but not that flyer. I just got it today.
You just got it today, all right.
I just got it this afternoon.
All right. We will get the flyer.
Yeah.
And then we'll send it out to everyone on the list to remind them of what's coming up. So, yeah. But anyway, MAS in general can participate in the VIP. How does that work?
Well, it was my decision. I would like to know about how many people are coming, but yeah, your group, since it's the group's name, I thought, yeah.
We'll solicit interest, and then if we have 150 people, we'll let Joanne know, and then we'll work it out. Just kidding. We won't bring that. But anyway, very exciting. Can't wait to see it. It's kind of like, was it 20, you said 2,000 feet from the sun to Neptune?
Yeah,
So-
to Pluto. Pluto's
Pluto.
there. Pluto was always there originally, so it's still
Pluto's
there.
They even included Pluto. They didn't leave out Pluto. So it may have been demoted, but it's still part of the solar system. Yeah, we can give a hand to Pluto.
As far as us older people are concerned, it's still a planet.
What's that?
As far as us older people are concerned, it's still
Yeah, it's still a planet, right?
You bet.
So, yeah.
I don't care what it is.
Put the half a mile.
It's round and it goes around the sun. So,
Tomato, tomato.
right, tomato, exactly. Tomato, tomato, stone, pebble, world, planet, what's the difference, right? All right. Okay, and with that, let's jump right in here. We'll go ahead and introduce our speaker for tonight and have a very intriguing presentation. And I want to welcome Dr. Benjamin Keller and his lovely wife to the Memphis Astronomical Society. And Ben joined the Department of Physics last fall. So again, we're kind of breaking him into the Memphis community. And I've got a brief description here for the benefit of our virtual audience. Dr. Keller is a numerical astrophysicist with a primary interest in the formation and evolution of galaxies. His research uses some of the world's largest supercomputers to simulate the gravitational collapse of gas and dark matter in the early universe, building up the structures we see today. Dr. Keller is a core contributor to the Gasoline 2 and N-Change simulation codes, and he's a member of the International N-Body Shop collaboration on simulation code development and applications. With these simulations, Dr. Keller studies how the lives and deaths of massive stars reshape the galaxies they form within by driving vast winds and fountains out of galaxy disks. These feedback processes are critical to establishing many of the curious features of galaxy populations we observe today, and for regulating the rate of star formation, without which our sun and the earth would not have formed. And tonight he's going to be telling us an intriguing story of the history of the universe from the Big Bang to beer. So ladies and gentlemen, please help me give a warm welcome. Mic you up here? Not at all. That's all it is. I'll put this on right here. Hopefully everybody. And you want questions at the end of the presentation?
I am happy to take questions at the end, in the middle, at the beginning, maybe not the beginning, but if you have a question, if something I've said makes no sense, or you can't hear me, or you want me to elaborate further, please just do so. I am really, really happy to clarify, I suppose. So let me just start the slides up here.
Chat.
Okay, great. So I'm just going to start, could you turn off your screen share here? There we go. And I'm just going to share my screen for the folks on Zoom there. And there we go. So, can you folks see this on Zoom? Excellent, excellent. So yeah, if I was giving a talk to a nice, serious, sober audience of boring Europeans, I might call this thing the emergent cosmos, how the laws of physics lead to the universe we see today. But this is a talk I originally developed for German audience, and so Germans are fun people. And if there's one thing the German people love, it's beer. So instead, I'd like to talk to you today about how those laws of physics have built up a universe that allows us to have this pinnacle of human achievement, beer. So really this is a thing that begins close to home, here on the planet Earth. So we're sitting here on the planet Earth, I'm standing, you're sitting, and you can see, of course, in this beautiful blue marble image from space that there's evidence of life on this planet Earth, that beautiful, beautiful greenery we see. And not just plant life and animal life, but human life, technological life, civilization. We've grown over many, many eons to have all kinds of complicated things, from the simplest kind of things like the water bottle I might drink out of here to the actual computer I'm presenting for you here on. And of course, there is a peak of our civilizational and technological development, that is beer. Nothing has yet surpassed the ability of the human mind to create wonders than this fantastic, fantastic drink. And so you're probably wondering why I'm talking about beer in a talk that's supposed to be about astronomy and cosmology. And really, the reason I want to talk to you about beer is because beer, like everything else that human beings create, could not be here if we weren't here. And if we aren't here, then the things that lead up to us aren't here. And there's a chain of cause and effect that leads all the way back to the very beginning of the universe that connect the simplest things, the laws of physics, to things that are complicated, human beings and the things that we've made. So I really have to start by asking, what actually do you need to make beer? Well, you need hops, you need wheat, you need water, but really what you need is schnapps. Not the delicious schnapps you might have at a German restaurant at the end of your meal, but schnapps, carbon, hydrogen, nitrogen, oxygen, phosphor, and sulfur. These chemical elements are the building blocks of organic life here on Earth. And really, this is the very first thing you have to have in order to have life and human life and all of the things that we've created. So really what this talk is about is how do we get these schnapps elements and all of the other elements of the periodic table? How do they come to be? And how do they come to be on this here planet Earth, which has evolved life, like plant life, and eventually evolved such complicated, sophisticated organisms to be able to take this plant life and turn it into beer. And beyond just the planet we live on and the materials that make it up, really we have this other piece of our solar system that's essential to this picture. Because if I go back to that wheat, and I go back to the people who use things with that wheat, ultimately that's all being fueled by energy coming from our star here. So now we have three pieces of the puzzle. We need the elements to make a beer or life in general. We need a place for that to happen, Earth. And we need a star that's really in the Goldilocks zone of being not too hot, not too cold. We don't want it so hot that the ionizing radiation of that star kills off any emergent life that might start. And you don't want it so cold that our planet is just a frozen wasteland. And you also want that star to last long enough for there to be the time for this process to happen. So really this story is about how do we get all of this? How do we get these chemical elements that make up our bodies and the bodies of every other living thing? How do we get a planet that orbits around a star that happens to be just the right temperature and have the right lifetime for all of these various processes to eventually lead to us today having this conversation? And this is a story that really does begin at the beginning. I mean, the best place to start a story is at the beginning. And so I'm going to be counting up here in terms of the lifetime of the universe. So we're going to start now at 0 seconds, the Big Bang itself, the point where the entirety of the space and mass energy of the universe is compressed down into a state of infinite density and infinite temperature. And one thing I'd like to do throughout this talk is not just tell you what I think I know, but tell you why I think it's true. So why do we think that the universe had a beginning? That it began at some sort of state of being very small, very dense, and very hot? Well, the biggest piece of evidence that really convinced most astronomers and physicists was an observation made by Edwin Hubble in 1929. And what Hubble found was that when he compared the distances of galaxies, shown here, and the velocity that those galaxies appeared to be moving away from us, the further you got back away from us, the faster galaxies appeared to be moving away. In other words, it looked like the universe was expanding. And if you run the clock in reverse, well, if it's expanding and you run it back far enough, eventually everything is piled up onto itself. Now you might also be wondering, how on earth did Hubble measure distances and velocities? Well, velocities are easy. You can can use the Doppler shift of light. Stuff that's moving away from us appears redder and redder. But Hubble doesn't have a ruler that he can run out with his measuring tape, his million parsec long measuring tape all the way out to these galaxies. Well, Hubble relied on a really, really important discovery by Henrietta Swan Leavitt. And what she found is that a certain kind of star called a Cepheid variable pulsed. It got brighter and dimmer over time. And as it got brighter and dimmer, the speed at which it did that told you its maximum brightness. And because of this, Hubble could then use those blinking Cepheid variables in distant galaxies to measure how distant they were. Because just like a candle, as I move it further and further away from you, appears more and more dim, these Cepheid variables appeared more and more dim the further they are away. So really, we call it Hubble's law, but it would have been impossible to determine without the work of Henrietta Swan Leavitt. So we're now at 0 seconds, and we know why we think there was this Big Bang. What happens next? Well, over the next 10 to the minus 30 seconds, 10 to the minus 36 seconds or so, we don't actually know. This is a period where the universe is so dense and so hot that both the laws of quantum mechanics and general relativity must both apply simultaneously. And no one has yet come up with a theory of quantum gravity that can do both of those things at the same time. This is really terra incognita for modern science, and it's one of the things that many cosmologists are trying to come up with ideas for today. Over the next while, we go from this incredible hot temperature, 10 to the 29 degrees Celsius, to a universe that's cooling down as it expands. Now, in the next second or so, we're now in the first second of the universe's lifetime. The universe becomes cold enough that individual quarks can coalesce into baryons. In other words, protons and neutrons. We're now at one of those schnapps, H. The first second of the universe is when hydrogen begins to form. Over the next few seconds to minutes, really the first 20 minutes of the universe's lifetime, the entirety of the universe has the density and temperature of the cores of stars. Nuclear reactions called fusion can slam those hydrogen atoms into each other to actually form heavier elements. Helium, tritium, which is an isotope of hydrogen, all the way up to lithium and beryllium. However, all this time, the universe is continuing to expand and cool off, which means by the time the universe is 20 minutes, it's no longer hot enough to continue fusing heavy elements, or light elements into heavy elements. So as of 20 minutes old, this is your periodic table. No carbon, no nitrogen, no oxygen, no phosphorus, no sulfur. We're in trouble if we want to have life. Over the next thousands of years, all the way up to 370,000 years after the Big Bang, the universe is very smooth and uniform, expanding and cooling until eventually it becomes cool enough that it drops below a few thousand degrees Celsius. And the ionized hydrogen that it's composed of recombines. That ionized hydrogen is opaque to light. The universe was as opaque as if it was made of a load of bricks. But eventually, around 370,000 years after the Big Bang, the universe becomes transparent. And the light from that early phase of the universe streams towards us today. This is what we see of that light today. And it's called the cosmic microwave background radiation. It was discovered in the 1950s and 60s by Penzias and Wilson, two radio astronomers who won the Nobel Prize for their discovery. Something that I'm sure they were really happy about, because their initial idea about why they were seeing microwaves at every piece of the sky was that the pigeons that roosted in their horn antenna must be leaving a lot of poop on it. So they scrubbed that antenna and still kept seeing that microwave radiation. And what they realized was they were seeing the leftover light of the Big Bang. So that CMB won them the Nobel Prize. And it tells us a huge amount of what we think we know about the cosmos today. You can see that it's kind of a noisy pattern. It kind of looks like the fuzz on an old-timey TV. And this pattern isn't quite perfectly random. In fact, it has patterns and correlations. And if you look at how intense those bright and dark patches are as a function of how big they are, so big patches are here, small ones are here, you can see it has this pattern here. We call this the cosmic microwave background's power spectrum. And it's a complicated shape, isn't it? It's not just like a straight line or a little dome. It's got these waves in it. The shape, brightness, and height of these peaks allow us to figure out what the universe is composed of. And being able to measure this, if you want to be able to measure small things, you need to get a good picture of that cosmic microwave background radiation. So over the course of the last 30 to 50 years or so I've jumped way forward in time now, we've launched satellites into space to measure the cosmic microwave background radiation at higher and higher angular resolutions. Think of it as a less and less blurry version of that picture. So we've gone from a sky that barely had any structure at all to one that has all of this detail that we can observe. And from that, we can actually measure what the universe is made of. So now we know that the universe is mostly made of this very mysterious substance called dark energy that causes the universe's acceleration to actually accelerate. The expansion accelerates. The ordinary matter, the stuff that makes up you and I, comes down to less than 5% of the universe. But what's interesting for you and I, organisms made out of this 5% of the regular matter, is that the rest of this stuff is important. That 4.9%, the little bit of it that ended up in us, wouldn't have ended up in us without the rest. So what happens after this period? What happens after this point at which, about 400,000 years, the universe becomes neutral? Well, we enter into an age called the Cosmic Dark Ages. Not because Rome falls, but because the universe is dark. There are no stars yet, no planets, no galaxies. The universe as a whole is filled with diffuse, cool, neutral, uniform gas. It's the most boring place you could ever be, aside from one of my classrooms. And this lasts for, we think, around 150 million years or so. And we think 150 million years because we haven't actually seen the end of it. We haven't been able to peer back in time to see that first generation of stars yet. But we're able to simulate what we think the physics should do. And so that first generation of stars that turn on, they begin ionizing the gas surrounding them. These stars form in clouds called halos of dark matter that collapse due to their own gravity and eventually allow new stars to form. And eventually, after a few million years of these proto-galaxies and proto-stars beginning to form, you'll see that this black emptiness of neutral gas is going to be replaced with orange diffuse ionized gas. This is a period called reionization, where the universe goes from being mostly neutral to mostly ionized, just like it used to be. And it will continue for the long future beyond us, because our universe now contains ionizing sources, galaxies, stars, and black holes that can turn neutral hydrogen into transparent ionized hydrogen.
Is that called the reheating phase?
Yeah, reheating is a similar term that relates to a potential thing that inflation could do back in that era of the big question mark. There's a lot of theories about what could go on there. We don't have a lot of evidence for them, but one of the things that could happen is the universe would become cooler and then, due to a thing called a phase transition, become rapidly hotter again. This period called reionization happens a lot later, and it's something that we are actually able to start looking at. Because, and perfect segue, thank you, I owe you. we now have this, the James Webb Space Telescope, or the Just Wonderful Space Telescope, as some of my friends call it. And the JWST could not have been a better Christmas present for astronomers across the world. I don't think there's been a Christmas better than December 25th, 2021, because JWST is the first instrument, the first instrument we've ever built that is able to start probing back to that era of reionization, the first stars and first galaxies. And we're starting to now see these little red nuggets all the way back to redshift 13. That's a galaxy that is existing 400 million years after the Big Bang, just a fraction of the universe's lifetime. These things are coming so fast and so many that a lot of astronomers are actually worried that our cosmology models might be broken because of this. And actually, this is something that very recently I had the pleasure of being able to investigate. So this is a plot from one of my most recent papers looking at what our cosmology models, computer simulations of galaxy formation, shown in each of these different kinds of colored plots, predict for the mass of galaxies at different times. And the black stars with the lines there are these actual new JWST observations. You can see we're getting close to the edge of what we predict. So far we're okay. Don't have to go back to the drawing board for cosmology yet. But if these things start getting pushed further and further up, we're going to have to come up with new ideas about the composition of the universe. And one of the great things about this that I had a lot of fun with is this is an opportunity I had to work with people I've been wanting to work with for years. Each of these different simulation projects comes from a different team across the world. And what's really cool, all of these simulations were done years to decades before JWST even launched. So this is a real prediction of what our ideas.
When you collaborate with these people, do you do it by email mostly?
Mostly by email, Zoom, and Slack, because these two are these first three are teams in Europe, this one in the UK, these two in Germany, this one's in Scotland. This is a guy I got to know very nicely in Heidelberg. He's French and he lives in Groningen in the Netherlands. And Romulus is from one of my good friends, Michael, who now lives in Ireland. So yeah, this was an international affair getting this paper done. It was great fun, great fun. So what happens next? Well, this whole process continues on. The next billions of years of the universe's history is a story of stuff collapsing down, gravity winning over pressure, and galaxies beginning to form, getting more and more massive through a process of accretion. You can see these streamers of gas going into this galaxy, as well as merging. You can see little galaxies coming into this new galaxy that's forming here in this simulation. Just to give you an idea here, 200 kiloparsecs is about 500,000 light years. So this is a big box, a big slice of the universe. And what you're seeing is the process that I studied, the process of galaxy formation. Those initial perturbations that we saw in the CMB eventually collapsed to form all this. Yeah?
So the way the simulation is made, those jets that we see from what look to be disks, are those active black holes?
That's a really, really excellent question. Those jets are those winds that I study as part of my research. Some of them are powered by black holes, others are actually powered by stars. And they're a really, really important piece of this puzzle that in a few moments I'll show you why are important. So now we're starting to form galaxies that have these stars in them. And one of the things that these stars are going to do is live their happy little lives and die. Eventually, those stars are going to reach the end of their fuel in their core. Their core will run out of the fuel that holds them up against gravity, and their cores will collapse. And this will trigger events called supernovae. Those first generation of stars probably went supernova very quickly. in only a few million years, because we believe that those first generation of stars were very, very massive, so they had very short lifetimes. Now this is cool. I mean, exploding stars is pretty cool. But it's also very, very important for this story of where we came to be. Because remember, at the end of the microwave background radiation, at the end of that period, the first 20 minutes of the universe's history, what we call Big Bang nucleosynthesis, we had a pretty boring periodic table. Hydrogen, helium, lithium, beryllium. 4 elements. And we're missing carbon, nitrogen, oxygen, phosphorus, sulfur, the stuff we're made of. This is where the rest of that stuff comes from. If we look at the periodic table, every single element except for hydrogen, helium, a little bit of lithium, and a little bit of beryllium, all come from the dying stars, either dying small stars, dying massive stars, even dying dead stars. Weird to think of something already dead dying again. But those cores that are left behind from stars can themselves explode due to different kinds of processes. Yep.
So I'm a slide or two back trying to figure out longer limit. You basically show galaxies coming into formation. You didn't say stars are happening and they coalesce together to form galaxies. You said galaxies are forming. So what's the
It's a chicken and egg problem, isn't it? Right? So that very first star to form in the entire universe, like that first generation, we call them population 3 stars. And they were forming in gravitationally bound objects that were so small, they likely only formed a handful of stars. So we don't really like to call them galaxies, we call them proto-galaxies or proto-halos. After that point, as things start getting bigger and bigger, as more and more material starts forming, really you're pouring the material onto galaxies, where then within that galaxy, it can cool and collapse even further to start to form stars inside the galaxy. So after that first generation, really the place in which stars form are inside of galaxies. There's of course some tiny exceptions to that rule, but 99.999% of the stars in the universe form inside of galaxies.
So kind of 2 follows. So this business of gaseous nebula, things that we like to look at with our telescopes, we say the birthplace of stars. So those are actually galaxies we're looking at.
Well, some are galaxies. So let's say we go to the Messier catalog. Some of them are galaxies, M101, M31, classic examples of galaxies. There's also star clusters, which are mostly not gas. And then there's things within our own galaxies, things like the Crab Nebula or the Orion Nebula, that are either the birthplaces of stars or the corpses of stars. So the Crab Nebula is a dead star. It's the result of an exploding massive star. Whereas Orion is a place in which new stars are forming. Yeah. So really, the gaseous nebula, they're the best things to look at, in my opinion. They're beautiful, and they're some of the things that tell us the most about how this process works, because you're catching either a star in the process or just after its death, or in the process of it forming. So it really tells you a lot, in many ways more than looking at a star does. So how do we know this now? I just told you all this stuff comes from here. How do we know this comes from here? Well, how do we know what anything in space is made of? How do we know what's inside the sun? Why do we think it's mostly hydrogen and helium and not cheese? Ultimately, it comes down to spectra. And probably the originator of the use of spectra to measure the chemical elements in stars is Cecilia Payne-Gaposchkin. She was the first woman to be awarded a PhD in Harvard, and many astronomers at the time considered her PhD thesis to be the greatest thesis ever done in all of astronomy. And what she did was she used a prism to split the light from the sun and use these things called absorption and emission lines. If you look at the relative brightness versus color or wavelength of light, you can pick up the telltale fingerprints of different elements. So now, long past Cecilia Payne-Gaposchkin's amazing early results, we can do this with Webb on galaxies that existed 13 billion years ago and measure how much oxygen's in that thing, how much neon. And one of the things we're finding is that as the universe ages, the periodic table becomes filled in. The earliest things are very low in these chemical elements, whereas the older, bigger things tend to be more enriched. And it's important, too, that those dying stars explode. It's not just good because it's fireworks. It's good because if those stars didn't explode, those chemical elements would be stuck at the bottom of them. They'd be trapped inside the core. So that explosion is what gets those chemical elements out into places where new stars are being born. So this dark, dusty nebula here is going to eventually start forming new protostars within these densest parts. And the reason this cloud is dusty, that dust we see in space, is very similar to the dust you'd find in a mine or a cave here on Earth. It's mostly carbon, iron, silicon. Really, it's dust made of rock. So as this gas begins to collapse down due to gravity, you start to form new stars. A second and third and fourth and fifth and sixth generation of stars. That first one began 150 million years after the Big Bang, but stars have continued to form all the way to the present day and will continue to form beyond that. And they give us this beautiful, beautiful kind of gaseous nebula that we can see. The reason we can see it is that it's lit up by the light of those young stars. And one of the things the light and deaths and explosions and winds of those young stars can do is actually carve holes in those star-forming regions. And beyond those holes in the little gaseous nebula that live within the galaxy, they can actually drive winds out of galaxies. This is my favorite galaxy. I'm a theorist, so I only really look at galaxies for pretty pictures and just to know that my models are correct. But this is M82, another Messier object, the cigar galaxy. And what you see in the red here is H-alpha ionized hydrogen emission coming from a massive wind kicked out of this galaxy. M82 is small. It doesn't have a very large, massive, supermassive black hole in its core. So this super wind is most likely driven by star formation, a burst of star formation. And one of the things that's really important about this feature that galaxies have is it slows down the process of star formation. Just like if you eat too much, you might get in trouble with your health. If a galaxy forms too many stars, eventually it's going to run out of fuel. That gas that you can see here is all going to be converted into stars. And one of the great things you can do about simulations is you can play God. You can say, you live in a universe that no longer has supernovae. What does that do? And when you look at this blue curve here, what you're looking at is how many stars exist within a simulated galaxy over time. And if you look at a universe that has no supernova in it, you form a ton of stars very early, and then you're dead. There's no more gas for you to form stars out of. Whereas if you include supernova using different types of models, you can have star formation that continues on. You can see it's no longer flat here. Well, this dead thing's a problem because this is where our sun forms. If this galaxy, like our own galaxy, had not had supernova driving these outflows from it, well, it would have run out of fuel a few billion years before our sun formed, and we wouldn't be here. So this whole process sets up something that we call the baryon cycle in galaxies. You saw it in that movie, but it's easy to understand. Gravity pulls gas down into galaxies where it forms stars. Those stars then die as supernova, and those supernova can drive outflows, some of which leave forever, never to return. But the important ones are the ones that recycle, returning that fuel a little bit later after that burst of star formation is slowed down, allowing the galaxy to regulate its own star formation. It's a regulatory process called negative feedback. And it's something, negative feedback is the kind of thing that exists all throughout our lives. It's what keeps your body temperature regulated. It's why when you go out when it's hot, you sweat and your cellular processes slow down to lower your body temperature. It's why the engine in your car doesn't spin up to RPMs that would tear it apart, because we built in negative feedback processes. Well, nature seems to have built in for us a negative feedback process in galaxies, which is nice because in a lot of ways other than this, it seems like nature is telling us, well, whatever this is telling us. But it's important too, not just to regulate the ways in which galaxies form. Inside those galaxies, the ways in which stars form is important as well. So this is a simulation that's done by my good friend Mike Grudich, and it's one of the highest resolution simulations of star formation done to date. It's a cloud of molecular gas that's collapsing and starting to form individual stars. Eventually you'll start to see them turn on as they blow gas away from their, due to their winds, jets, and radiation. There you can start to see those first little baby stars. Well, these baby stars are very messy eaters, and as soon as they start to eat and accrete material, they're going to start messing up their environment. You can already start to see this hot bubble of ionized gas being formed, and eventually, as more and more material fall on to these accreting protostars, they're going to start blasting out their own little jets. There's the first one starting there, and here, coming from below, is a big one, a big bunch of them. These jets are eventually going to scour this region of all of the gas. Here you can really see it starting with this young star cluster up here. Eventually this too is going to shut down star formation in this cloud. And it's going to act in the same way to regulate star formation at the small scale. So we've got these processes of feedback all the way down here. And what's important about this is it tells you what kinds of stars are going to come out of here. This competitive accretion and feedback is eventually going to tell you how many teeny little stars, like the sun, you get, versus how many giants, 100 times bigger than the sun. Now, it's important that we know that there are these different kinds of stars, and I promised you, I'd tell you a little bit about how we know these things. Well, the classification we have for different kinds of stars based on their brightness and size was also invented in the early 20th century by actually a deaf astronomer by the name of Annie Jump Canyon. Her story is very interesting. How many people know what a computer meant in 1900? Okay, we've got some ideas. Well, what's a computer if it's 1901? Her. Yes, Annie Jump Canyon was a member of the Harvard computers. Computers at that time were mostly women who worked doing the tedious calculation for the men who were allowed to get all of the credit of making these big discoveries. But Annie Jump Canyon was more than just a mechanical computer. She actually made major discoveries of herself. And one of them was coming up with a way of classifying the main sequence of stars. This is a relationship between the brightness and luminosity of stars called the Harvard classification, named after the institution she worked at. Of course, Harvard steals. We don't call it the Jump Canyon classification, even though we should. You know how the Ivy Leagues are. But these are the biggest stars. These are the smallest, all the way down this main sequence here. And what that process we saw in the previous simulation does tells you how many stars end up here versus here. Because we wouldn't want to be in orbit around a star like this for a couple of reasons. One, we'd have the worst sunburn ever. So bad mostly that our skin would actually be ionizing and turning into a gas, which would be bad. Also, we wouldn't be here at all having this conversation because our star would have died 4.5 billion years ago. The most massive stars die as supernova 4 million years after they form. And as we're about to see, that is not enough time for you to get a good mug of beer brewing. So, we're now at the point where we're talking about stars and the formation of our solar system. We've now gone 9.5 billion years after the Big Bang. And I'm now going to start showing how many years ago, because we're closer now to the present than we were to the beginning of the universe. So in those forming clouds of stars. We didn't zoom in close enough to see, but those stars are surrounded by what are called protoplanetary disks. These are things that are made of a rotating cloud of gas losing its energy and collapsing in the same way that a pizza, you throw a blob of pizza dough, it flattens out into a disk. This is where the planets of our solar system will form. And once again, I promise to tell you why we think this is true. Well, this is an easy one, because we've seen them. And we've seen them as of basically when I did my PhD. Prior to that, this was just speculation. So in 2011, a really important telescope opened up in the Atacama Desert called ALMA, the Atacama Large Millimeter Array. And this is one of the highest precision telescopes in certain wavelengths that exists today. And what ALMA has given us, among many, many other things, is all of these beautiful images of protoplanetary disks. We now have dozens of these things. And this is a new solar system being formed. The gaps in here, these holes in these rings, are being carved out by new planets forming around these brand new nascent stars. So you might think, okay, we're done. We got our schnapps made in the cores of stars. We got a young star that was able to form recently with all of the right components. Great, let's start brewing. Well, 4.5 billion years ago, the Earth was not a very friendly place. As that Earth forms, it's forming from asteroids, pebbles, boulders slamming into each other. And so the first 500 million years of the Earth's history or so is called the Hadean epoch, because it's much like the old Greek idea of the underworld. Sulfurous, lava, hot, scalding, awful place to be. And it's also the time in which the moon would form. So we suspect that the moon actually formed out of a giant impact based on what we've been able to determine from the isotope compositions of the rocks that were brought back by the Apollo astronauts. And this is something that we're able to simulate as well today, this giant impact process. So as you can see, even if things were nice on Earth before this impact, not so nice afterwards. And not so nice for a long while, because you can form your nice little moon, but then, here comes the rest of that impactor. And this cloud of haze you can see around here is actually vaporized rock. So even if the Earth had started to cool during the Hadean period, when this giant impact occurred that formed the moon, it would have resurfaced everything. If you were the first life form that had begun before the giant impact, well, none of your descendants are around today. So how do we know anything about the early universe then, if the whole surface of the early solar system, the whole surface of the Earth had been constantly whacked and walloped and melted and mixed? Well, not everything ended up in the Earth. We have meteorites, like this piece of the Allende meteorite, that can act as time capsules to tell us what the components of the early solar system looked like. And it was these kinds of things, meteors and comets, that actually brought the water to the Earth's surface after it finally cooled from this violent Hadean era. Eventually, you had enough time where this chemistry that could exist within that early, wet, but dead Earth to start to form the first single-celled organisms. We think that they probably formed somewhere around 4 to 3.5 billion years ago. We don't have, obviously, a fossil of the very first organism, but we have these things called stromatolites, which are fossilized single-celled organisms from around this time. They exist in certain parts of the world. This one here is in Australia. Now, 4.5 billion years ago, the Earth forms. 500 million years later, the first life begins. Well, what's the holdup? Why didn't we have beer 3.5 billion years ago? Well, as you know, we brew beer out of plants. Wheat, hops, oats, rye, emmer, for example. And these first organisms probably weren't plants. They probably couldn't do photosynthesis. We believe that photosynthesis probably arose around 2 billion years ago. At first, not in plants, but in bacteria called cyanobacteria, or blue-green algae. One of the impacts of this if these things were very successful, is they may have pumped so much oxygen into the atmosphere that they caused massive global cooling, freezing the Earth's surface. This might have been the first time where an organism on Earth had caused major climate change, only in the opposite direction. The reason we suspect that is if you go back to rocks around 2 billion years ago, you find these banded iron formations. They're rust. Before our atmosphere had lots of oxygen in it, iron would never rust. So these banded iron formations are most likely the dissolved iron of the ocean, now exposed to all of this oxygen, turning into rust and sinking, settling into the ocean floor, and leaving behind these bands of rust. Now, again, you might think, okay, we're good. Well, cyanobacteria don't have any hands. And even if you could make beer without hands, you can't drink it without at least something to hold the mug. So you need to get animals. You need multicellular life. And we think that multicellular life really had its first beginnings somewhere around 500 to 600 million years ago, and really blossomed in the early ocean in this period called the Cambrian explosion. Some of the first complicated organisms that we have fossils for come from this period. If you ever have an opportunity to visit Alberta in Canada, go to the Walcott Quarry where these animals were first discovered. You'll see fossils that will blow your mind, just scattered across the ground. Weird animals, things with 7 eyes, things with walking on 14 legs. Very, very strange animals. Not us, but perhaps some of our ancestors. Now eventually we're going to have to get to the point where we got the things to grow to make the beer. So during the Devonian period, about 100 million years later, the Earth's surface, all of this complicated Cambrian stuff is happening below the Earth's oceans. Devonian period is the explosion and efflorescence of plant life across the Earth's surface. This is the point where really plants dominate the globe. And the descendants of these plants, they're going to be those things we're going to start brewing. But what about us? What about us, the brewers? Well, mammals. Mammals are starting to begin to evolve as well. A few 100 million years later, we're starting to get things like cyanodonts, these weird reptile, mammal, transitional forms that are likely the earliest mammal-like animals. These things are eventually going to start over the next few 100 million years, splitting into all the different kinds of mammals we have, eventually leading to, about 12 million years ago, the ancestors of early modern humans. So some of those ancestors branched off to become gorillas, some branched off to be chimpanzees and bonobos, and by them I mean their long, 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 long dead ancestors. But one of them branched off to become us. And those us, starting to really become anatomically modern humans, perhaps only a few 100,000 years ago, well, they began in Africa, in sort of the rift valleys here of Central Africa, and very quickly branched out, spread across the entire globe. It's pretty amazing to think about the fact that there were humans on every continent except for Antarctica thousands of years before the invention of steamships or electricity or any of the things that we would think are modern conveniences. And these people did stuff. They were anatomically modern, which means they weren't stupid just because they walked around and lived in caves and said, ugh. They made art. 400,000 years ago, we had art in cave paintings in the south of France. They made tools and statuaries, stone tools that we can find all across the globe. Statues of lions in Germany. Interesting to think that 400,000 years ago, there were lions and elephants as far north as Germany. And eventually, these people settled down. They invented a new technology, something even more useful than stone tools or cool statues of lions. They invented agriculture, and they began to move from a kind of lifestyle where you ate and lived off the stuff you found in the wild to eating and living off of the stuff you grew and the animals you husbanded. So 10,000 years ago, is where we find the earliest evidence of permanent settlements of human beings. This one here is from Anatolia in Turkey. And these people had revolutionized the way they lived. They now no longer had to hunt animals, they simply bred animals. They no longer had to gather wheat, they grew wheat. And this 10,000 year ago era is called the Neolithic Revolution. It's a revolution because they've completely changed the way humans live. We are now a species that lives in cities and settlements, that doesn't move around with the climate, but actually plants our feet somewhere, builds things that can be left behind 10,000 years ago. And this is really the period at which beer begins. Because we think that one of the first applications of agriculture was to brew this stuff. In fact, one of the oldest bits of writing we have is a 4,000-year-old Sumerian tablet that's a receipt for best quality beer. We have evidence that the Egyptians brewed and in fact lived off of, in many cases, a kind of wheat beer that was almost more like a liquid bread. And so we finally now, 10,000 years ago, or in other words, 14 billion years since the beginning, have reached the point where the world around us looks the way, more or less, with a few tweaks here or there, the way it does today. Of people living in homes, trading with each other, eating and brewing food, things like beer. And it's really a story that begins all the way back at the Big Bang, that relies on the formation, lives, and deaths of those first galaxies and stars, the formation of life here on Earth, and the way in which our planet began, and ends with us here in the present day. Now, if you want me to go beyond that, well, that'll be another talk. Because now we finally reached a point where we know where this came from. So, if you have any questions, please. Yeah.
Excellent talk.
Thank you.
Thoroughly enjoyed it. Can you go back to the slide with the animation of the crash test Earth?
Oh, yeah, the giant impact. Yeah.
So it's a two-part question while you're getting there.
Yeah.
So first part is, were you implying that that crash is what led to the elements necessary for the Cambrian explosion?
Oh, no, it was not that. Actually, the moon forming impact might not have been important for the formation of life. It's just something that we think
That
happened
happened
to us.
prior.
Why we have a moon that has the properties that it does. So the Earth's moon is kind of weird compared to other moons. It's very big relative to the planet, and it rotates relatively fast. And so there's been, like, prior to people bringing stuff back from the moon so we could do geology on it, there were competing hypotheses. This is the one that we think is most likely today.
Okay.
The moon might be important for life, though, because one of the things that my former institute does is work on astrobiology and origin of life. And Ralph Pudritz at McMaster University works on a hypothesis that life may have begun because of tides pushing water onto the shore and then pulling it out, so that you had successive wet and dry periods that could allow certain kinds of chemistry to occur that would never occur if you just had dry rock and just had wet rock.
Which is from the tidal shifts of the moon.
Exactly.
But I guess the second part of my question was going to be, has anyone made any efforts to trace back the trajectory of that impact?
That's what simulation, yes.
Okay, and then the follow-on to that one was going to be, because like you talked about the flickering, which is kind of similar to the theory of the Kardashev. If you could find a flicker, that would be a civilization that had generating solar from the stars.
Yeah. So the simulations like this are one of the ways we can try and guess what what is called the impact parameters of this were, because obviously you can't do it in a lab. I live here, I don't want someone doing that to the Earth. And we can't really see this happening other places in the universe because it's probably a very rare occurrence. But I can simulate 100 different possible ways for this impact to occur and see which ones produce a moon with the orbital parameters that we like. The other question about those Cepheid variables, that was the flickering you were talking about. We think that those Cepheid variables, if I go back to the image, you saw that that variable star was surrounded by stuff. It didn't look like just a point of light. It looked like a star surrounded by a nebula. Cepheids are dying stars, actually. They're blowing out their outer layers, and so they're in a process where they're out of equilibrium, where the star begins to collapse, but it's not yet dead. So as it begins to collapse, it gets hotter, and so it expands, and then it cools off, so it begins to collapse, and then it expands, and so it's going to continue doing this, and each successive burst is blasting out outer layers of the star. But techno searches for, well, what are called searches for techno-signatures are actually a somewhat new and a hot field in astronomy today, because our surveys are getting so big and so wide, we might be able to actually get things that are really, really rare. So there have been people looking for things like, do we see any stars that are really bright in the infrared, but have no visible light, almost as if they're surrounded by a sphere of metal.
Right.
There have been searches for things like Dyson spheres. So far we haven't found anything definitive, but going back to like the Webb telescope, we might find life on other planets now with tools like Webb by looking at the emission line or the absorption spectrum. So if I go back to that spectrum, well, you can look at the tiny fraction of light. If here's your planet and here's the star, there's a beam of light that you can see is hitting over there. Well, if the planet passes in front of the star, it blocks out the point of light. But just before, that light passes through the planet's atmosphere. And so if we find a planet that, say, for example, has industrial pollutants in its atmosphere, that's probably a good sign of light. More likely, we'd find a planet with lots of oxygen and methane also in its atmosphere, which can't exist in chemical equilibrium, meaning something has to be making it, like photosynthesizing life. So this is probably the first evidence we're going to have, and I would not be surprised if it happens in our lifetime.
I'm having trouble. I see 4 bands of hydrogen.
Yep. Yep, 1, 2, 3.
Can you explain that? And same with
Yeah.
oxygen.
Absolutely. So it's not...
Excuse me, could you repeat the questions?
Absolutely. Sure. So the question is, if I look at this, why are there 4 points here for hydrogen, 2 for neon, 4 for oxygen? And the reason is actually really, like, there's 2 things. There's the reason why, but then there's the thing that does for it. Let's imagine that there's only 1 point. 1 point for hydrogen. So something that's moving towards you is going to have that blue shifted. It's going to move. And if it's moving away from you, it's going to be red shifted. Which means if there was only 1 peak, 1 line for each element, you could never know what the chemical composition in something is, because the red shift could put the hydrogen line where the oxygen line should be, or put the oxygen line where the neon line could be. Every element has a whole cone of these spectral lines, many lines, that each one corresponds to a different energy level for the electrons in that atom. So the hydrogen lines here, you can see the wavelength is going down here. So this is a high energy electron, this is the lower energy level, this is the lower one still, and this is the lowest one. This would be, I think, H alpha. So if you've ever heard of something like the Balmer series with hydrogen, where you get, if you heat up hydrogen and pass it through a prism, you get spikes of color. That's what you're seeing here, is those spikes of color. Because there's more than 1, that's how we can measure redshift, and that's how we can be confident we're actually seeing the light from an element that we think it is. Because even though this cone moves back and forth, the gaps between these lines never changes. The whole thing gets shifted together. So you just line up where the gaps should be, and you know what element you found. Yep.
From one of our YouTube servers. Sorry.
No problem.
How did dark matter form, and what effect does it have on galaxy location?
Oh, baby, that's a great question. Oh, that's a great question. If you could tell me how dark matter formed, you would win a Nobel Prize. Because we don't know how. We think that it probably formed going way back in the early universe to this period where we don't really know what the physics was, because we don't really know what kinds of particles could spring into existence out of a soup of particles that's this hot. So one of the main theories for how dark matter forms is that it's what's called a thermal relic. It was formed in the time when the universe was very hot, and it has that temperature left behind from that period, and it no longer forms or annihilates because the universe isn't dense enough for it to interact with many things. As for what it does, what dark matter does is it takes these peaks, which the red guys here are over density, slightly denser regions of the universe, it takes those peaks and it turns them into bigger peaks because gravity wants to pull stuff down. And dark matter has mass, so gravity is really given a boost, an assist, by having a universe that isn't just filled with gas, but is actually filled with a ton of dark matter. So everywhere, what you're seeing here is gas in this simulation. The color is from gas. But if we were to look at another component of the simulation, everywhere these galaxies are forming, they're inside a halo of dark matter. And these filaments that you see here are actually a kind of cosmic web made of collapsed dark matter. Yep.
You said, I believe you said just a few seconds ago that dark matter, that theorized dark matter formed in like 10 to the negative 39 seconds or whatever, and then that it stayed relatively constant, neither annihilating or destroying since then. So like whenever we look at the time records with things like the James Webb, does the amount of dark matter measurable indirectly via whatever indirect measurements stay constant time-wise?
That's a phenomenal question. So does the amount of dark matter in the universe stay constant? It depends on what you mean by amount. And this is an interesting thing. So let's say you have a box with 10 marbles in it. If you make that box bigger, you've still got 10 marbles in it, right? But the density of marbles goes down. So as the universe expands, the total amount of dark matter, the total mass of it, we think is constant. The total density, though, is going down. Dark energy, though, that weird thing that we think makes up the majority of the universe, has a constant density, which is very weird. Hard to imagine something with a constant density, but that means that as the universe expands, there's actually more dark energy, that it's somehow tied to the nature of space itself, rather than some stuff that's bumbling around in that space. Yeah.
Okay, so is the matter settled then on dark energy? Are we looking at a cosmological constant and we're ruling out quintessence or dynamic dark energy? Is it constant, or is it still debatable?
So this is possibly one of the things that could break our idea of this just being a simple cosmological constant, because if more galaxies get detected by James Webb that are well above what the simulations and what cosmological models with regular lambda cosmological constant dark energy can predict, one of the ways to fix that, to start forming bigger galaxies earlier, is to modify the form of dark energy. One of the kind of my particular favorite one, although I'm fairly agnostic on this, is a form called early dark energy. But to really nail that down, there's a couple of things we need, and one of the big ones is called precision cosmology. Basically, if you look here, these error bars are huge. And so we need these error bars to be very, very small, because right now, the only kinds of modified versions of dark energy that are allowed are ones that are pretty close to regular cosmological constant dark energy. The variations between them can't be that big because we have that really, really good power spectrum from Planck. Yeah. But I would say bet on lambda, but don't bet too much.
We hope it's lambda, because if it's not, it's going to make the problem much more complicated.
Exactly, yeah.
So how come we see regions of high densities of dark matter, but not things such as a dark matter star, where those densities become trapped in a fusion?
That's a fantastic question. Why do we see dark matter halos, like denser regions of dark matter, but not dark matter stars? And that comes down to how stars actually form. So if we look at, say, the Orion Nebula here, gravity's going to want to pull this in, right? And so if this thing is in equilibrium, it's at the point where pressure pushes out as strong as gravity pushes in, what are you going to have to do in order to get gravity to win? Lower the pressure. So the way that gas lowers its pressure is gives off radiation. The fact that we're seeing the light coming from this means it's losing energy. Dark matter doesn't give off radiation, it doesn't interact with radiation, which means if you take a cloud of dark matter and squeeze it down, the pressure of it is going to increase. The individual particles are going to be jostling around faster. But they have no way of losing their kinetic energy. And so once a dark matter halo becomes something called virialized, where there's a balance between its kinetic and thermal energy, you can never throw away its kinetic and potential energy, gravity, potential, kinetic moving around. There's no way of throwing away that kinetic energy, which means if you squeeze it, it will just oscillate. It will never collapse. It will ring like a bell, but it'll never collapse down to forming dark matter stars. So yeah, if dark matter either gave off radiation, collided with regular matter, or collided with itself, it would be able to form dark stars. But the fact that we don't see dark stars, which you could see them by gravitational lensing, but we've ruled out that there can't be very many of them. If they exist, they're incredibly rare. That probably means that dark matter almost never collides with itself.
And I'm sorry, this begs another question. So how come we don't see increases in the masses of things such as supermassive black holes from the accretion of dark matter?
They do. Supermassive black holes in a regular dark matter halo actually produce something that's one of the ways we're trying to detect dark matter, called a dark matter spike. They pull that material in around them and produce a massive increase in the density of dark matter. The reason the black hole itself doesn't grow very much from accreting dark matter is the same reason we don't have dark matter stars. Right here in this room, there is dark matter. Everything else in the room is far denser than that dark matter. The density of dark matter even in the center of galaxies is really low, way lower than the density of gas. So it's like you're eating a meal and it's like, have one tiny little grain of rice here from the dark matter and then the biggest bowl of chili you've ever seen from the gas. It's like, well, the thing that's going to fill you up is the gas, not that little grain of rice.
Makes a lot of sense. Thank you.
Thank you.
Yeah. Is gas coalescence a primary way that gravitational quantity occurs in the formation, early formation?
Absolutely. So the first thing that gets things started in the early universe is dark matter kind of accelerating ahead of the gas, because around when the cosmic microwave background is emitted, the universe is still pretty dense and pretty hot and high pressure. So there's a quantity that we use in astronomy called the Jeans length. It's the smallest thing that can that will fragment down. So everything bigger than that can fragment down. Jeans length in the early universe is huge, gigantic. And so everything should be really, really smooth. You shouldn't see lots of little clumps. But the dark matter, because it doesn't feel the thermal pressure of the gas, can actually start ahead of the gas to start forming structure, and then the gas can catch up because it feels the gravity of the dark matter.
What are the so-called perturbations that they talk about in the early seeding galaxies that they mentioned?
Great question. So visually, they're these things. It's the things that make this not smooth. It's the little lumps and clumps that you can see in here. Quantitatively, it's the structure that makes up this power spectrum. Where it comes from, though, unfortunately, goes back to that big old question mark. We don't know the origin of the early perturbations. One of the theories for where that comes from is quantum fluctuations that were expanded to large scale through a process called inflation that had the universe expand many, like 10 to the 100 times bigger in the first 10 to the minus 30 seconds or so. It could blow up quantum fluctuations that would give you kind of a Gaussian-ish power spectrum. The reason this isn't Gaussian, for those of you who don't know, is just a bell curve, is these ringing here are actually like sound waves passing through the universe. This first one here is called the acoustic peak. And it's generated by sound waves moving through the universe. So what we're seeing here is a combination of this mysterious physics of what generated these early perturbations that we don't really understand yet, plus some really amazingly simple physics operating on the scale of the entire universe. So things that are simple, like gravity collapsing things in a linear mode, where nothing collapses all too much, it just gets moved around a little, and sound waves, which are pressure waves in a linear mode, where nothing gets too high pressure, it just moves around a little. So it's remarkable, quite frankly, that the entire universe is really, at this point, the simplest thing that we can even reason about in physics. This is like, this is actually the spherical cow you hear joked about in physics. The universe itself was a spherical cow at this point.
Just great, is that look like some of the radio events that galaxies used to say?
Yeah, well, that's a great question. Noticing that it looks a lot like the radio maps of the galaxy. This is a radio, it's a microwave map. So this is generated by, one thing you're probably noticing is where is the galaxy in the plane? There is an army of scientists who worked on the Planck mission to subtract out the background. Because we don't want to see the galaxy, we want to see what's behind the galaxy. And so, yeah, if you did just a microwave map of the universe without that subtraction, you would see this beautiful galaxy with like bubbles and spurs and things like that. Yeah.
I remember back when I started out in astrophysics.
Yeah. Oh,
I
cool.
first started going to college, then I changed. And I remember dark matter was a big bone of contention for astrophysicists. They couldn't even prove it existed.
Yeah. Still is, less than it was, but it's, I would say it's, I would say that the preponderance of evidence, I wouldn't bet a house on dark energy just being a simple cosmological constant. I bet my kidney that particle dark matter exists.
Oh, so that's my next question. Okay.
Because
it's about what?
yeah, the reason I bet my kidney is this. You don't get this shape, the ratio of these peaks, without having a large fraction of the matter in the universe be dark. In other words, not interact with radiation and with thermal pressure. And look how small the error bars are on here. They're big over here. That doesn't matter. What matters is the difference between here and here. Look at how tiny those error bars are. This is really the most precise measurement in all of astronomy.
Like I said, we didn't have those.
No, we didn't have this until just, this is Planck, and this is from 2013. Yeah. Yeah, it's remarkable how much it's changed.
Okay, I'm glad you brought that up, because I'm like you. I'm not sure I would bet my kidney, but I'm in the particle category as well.
Yeah.
However, there is some disagreement. I'm not going to point out any names, but there are some who still think gravity needs another term,
Yep.
and you haven't found any WIMPs. It could be axions. It could be sterile neutrinos. What's the latest? What direction are we heading?
I'm fine with axions or sterile neutrinos, because they would still be produced in the early universe. Basically, I need a particle that makes up about like at least 3/4 of the mass in the universe that formed at the time or before the CMB existed. So anything that does that gets these peaks right for me. So axions would do that, sterile neutrinos would do that. What doesn't get that is modifying gravity. So if you say, what if there's no particle dark matter at all? What if it's just gravity doesn't behave as Newton and Einstein predicted, but behaves a little differently to give you the effects that we see that made us first think of dark matter? Well, that can never give you the precise match of peak positions and sizes here. Maybe not never. Maybe you could really, really abuse the model and add 14 different fudge factors and tuning parameters. But this is just a beautiful prediction of what we call the 7-parameter model for cosmology. Basically, the only thing that you have to tune to get this right is How much dark matter do you have? How much dark energy do you have? How much regular matter? You don't have to make up new ways in which it behaves that, oh, maybe on a Thursday it only moves to the left and that gives you the behavior you want. All you need to do is say how much of it, and really what you're doing by saying how much of it is measuring how much of it using the shape of this observation. Yeah. So I'm fine with access. In fact, one of the things that I might be working on in the next couple of years is possibly adding in axion-based dark matter to some of our simulations, because one of the weird features axion dark matter has is that it's so light, it has quantum effects on the scale of galaxies. So you can have quantum interference on the scale of galaxies that could have observable astronomical features to it. I wouldn't bet the house, though, that it is axions. It's a possibility.
Aren't axions too light and unstable to fit the characteristics of a dark matter particle?
Very good question. Why do we call this thing lambda C, cold dark matter? Well, one of the reasons we prefer cold dark matter is that if dark matter freezes out of the universe, the early universe, its mass tells us how fast it's moving. Big things would be moving slow, light things would be moving fast, if it's produced through what's called a thermal process. And if things are moving fast, where you have hot dark matter, then this process is going to be slowed down greatly. These little things that start to coalesce, the dark matter in them is just going to free stream out, and they're not going to be able to collapse. So a universe that has hot dark matter instead of cold dark matter is a universe where the first things to form are giant galaxies that then fragment. We think that the way the universe formed is that it first formed small galaxies that merge to build up bigger galaxies. We call that a hierarchical picture. If that dark matter was hot, we would have an anti-hierarchical picture where you get big things uniformly collapsing and then little parts of them fragment, so that things like the Magellanic Clouds, we think that the way that the Magellanic Clouds came to be near us was that they formed far away and that they accreted inwards. In an anti-hierarchical universe, all the material that made up the Milky Way, probably Andromeda, and the Magellanic Clouds would have collapsed into one big thing very early on in the universe, and then fragmented. One chunk would form Andromeda, one chunk would form the Milky Way, smaller chunks would form the Magellanic Clouds, and one of the features that gives you is very different looking distributions of where galaxies are, how fast they're moving to each other. We've ruled that out essentially. But axions can actually form through non-thermal processes, so they can be light but cold. They need to be cold, but there's a couple of outs that you can form them while still being lit. And of course, we don't know that axions are even possible. Axions are a hypothetical proposed extension to the standard model. We don't know if axions even exist, let alone whether or not they are the thing that makes up dark matter.
But we could detect solar axions and prove it.
We haven't.
Right.
We could. One of my colleagues at the University of Washington is working on an experiment called ADMX. Axions are a really attractive dark matter candidate particle because you can detect them with an instrument the size of a refrigerator instead of the size of this entire building.
Yeah.
Yeah, so they're cheap to detect, but we haven't actually found any yet. But if we do, then we know what it is. That's the scary, the terrifying thing that keeps all of us up at night is we have all of this indirect evidence for dark matter that's so compelling, and we've never seen the stuff.
Yeah.
That's scary. That's really scary. It's like we walked into a room and there's blood all over the walls. There's a knife stabbed into the door. There's ripped clothes and money pulled out of a wallet. But no one's missing. No one seems to be in any kind of trouble. It's like it looks like a murder happening in here. There's everything you could think to make you think that there's a murder happening here. Where's the body? And that's the state we're in with dark matter.
Yeah.
Yeah.
So you mentioned about the inflationary era and the reheating.
Yeah.
how does the collapse of the Higgs field of the current value fit into that timeline at all? Are those the same event, or are those different events, or are they simultaneous?
That's a good question. I'm not an early universe cosmologist, so I don't know if I could confidently answer that question without making something up. I'm more of a, really my expertise ends at the first 10 to the minus 36 seconds of the universe. After that, I have a pretty good understanding of how things work, but that first, really honestly, the first 10th of a second, it's a real doozy.
For the kids in the room, how old were you when you started to evolve with this passion and decided that this was the niche you wanted to fill?
Oh, good question. When did I decide this is what I wanted to do? I've always known I wanted to be a scientist since the idea of a job was a thing in my head. The first time someone asked me what I wanted to be when I grew up, it was a scientist. It started out with a chemist, and then a biologist, then a microbiologist, then a chemical engineer, then a computer scientist, then a quantum theorist, and only until I was in my undergrad when I started to really actually learn a lot of the true things about how to work with these ideas, beyond just, honestly, the kind of stuff that I've told you about what we know, but really how we figure that out and how we figure out new things. That I tried different fields. Like I thought at the time that I was going to go into quantum information science because I really wanted to be the guy that built the first quantum computer. The problem was that was boring. And astronomy research was really fun. And so I'd done a little bit of research as an undergrad, working on radio astronomy, looking at the jets that come out of supermassive black holes, and I caught the bug. So I went to do my PhD in astronomy. I figured I might as well technically it was a PhD in physics, but I figured, hey, I love computers, I really want to combine these things. Let's find a way where I can do programming, I can dig in, I can get my hands on supercomputers that I never would be able to play with otherwise, while still learning something about the universe. So that's why I chose to go into this field of numerical cosmology or numerical astrophysics. Because it kind of let me keep one foot in the computer pool and one foot in the physics and astronomy pool, and really I've been able to have my cake and eat it that way.
One question. Expansion.
Yes,
Is
expansion.
it current thought about most people that we're going to keep expanding forever? Let's say that it's 13.8 billion years from now.
Yeah.
And we can't even see Polaris because we're going away from us faster than light travels. I mean, is that the thought, or is the thought someone will stop that?
That is a really dismal and unfortunate thought, I'm afraid. What is the ultimate? I'm not saying that's a bad question. I'm just saying the answer is unfortunate. So the question is, what is the fate of the universe? And this pie chart I hear, it adds up to 1. And that's more than a coincidence than just the fact that pie charts always have to add up to 1, I guess. We think that the density of the universe, when you add all of these things up, works out to exactly the critical density to give the universe a flat curvature. If it was a little bit less, the universe would have something called an open curvature, where it would expand forever, but it would expand at an exponentially increasing rate rather than just a geometrically increasing rate that dark matter will give it. Flat means because it has dark matter, it will expand forever, and if we had a little more, if instead of this adding up to 1, it added up to 1.00000, as many as you want, 1, then eventually it would recollapse. We'd have a closed universe. So we think that we have, and this is maybe a hint about that early universe, that it's right exactly at 1. That seems like a huge coincidence. There's a lot of numbers besides 1. And the fact that it's 1 seems like a bit of a coincidence. So that might tell us something about the early universe. But the fact that it's 1 and the fact that we have a cosmological constant means the universe will keep expanding. It'll expand faster and faster. Eventually every galaxy will be redshifted out of the observable range. Eventually the stars in our galaxy will be not just redshifted apart, the galaxy itself will be unbound. And because we've got a long time to go, long before that happens, there will be no more star formation. Eventually, that baryon cycle process of negative feedback, it's doing its best to try and keep things going slowly. Not that it's it's mindless, it's just the process of physics. It can't go on forever because there are things, baryons being put into forms that don't get recycled. Black holes, white dwarfs, neutron stars, they they don't recycle. So eventually, long time, I can't tell you exactly the number off the top of my head, but eventually all of the stars in the universe will have exhausted themselves and there won't be enough dense gas left to form any new stars. The only collapsed things in the universe will be like cold, dead planets, asteroids, black holes. Eventually, the black holes themselves will radiate away because of a process called Hawking radiation. Most likely, we think that protons are unstable, so eventually protons are going to decay into photons. The ultimate state of the universe, we think, is a very cold, very uniform soup of photons. Very boring, very boring. But that's only using our current understanding. The fact that we don't understand the first little slice probably does mean we don't have a very good understanding about the last big slice. So I wouldn't, like I said with the other things, I wouldn't bet my house on that being the ultimate state of the universe, but that is kind of what the current understanding of physics predicts.
I got two more questions, but I want to see if anybody else is
I just want to say something. I read the article in Quantum magazine about you and your collaboration.
Oh, thank you.
Congratulations, that was a great article.
Thank you.
Quantum magazine is an excellent,
fantastic publication.
Magazine, science magazine. So I was really pleased to see that. And the University of Memphis being mentioned.
So again, for the younger folks in the audience, any suggestions, guide if they're interested in this area to explore more on their own? What kind of, are there structured courses or are there just research on your own?
In a lot of ways, we're in a golden era. Like, it's very, very easy to learn about these things. There are places like Quantum Magazine, for example, that does really excellent in-depth reporting about new science in a way that's understandable but isn't dumbed down, and even more importantly, isn't wrong. One of the things that makes scientists pull our hairs out is when the press release comes out, it's like, oh, that's a little bit wrong. And then it gets to an article, it's like, oh, that's a lot bit wrong. And then that article is the basis of another article. It's like, that's nothing like what I said I did. So it's important to try and find good resources that are reliable. Quanta is one of them. There's also a lot of stuff on YouTube now with channels like Big Think. I would say, though, the best thing to do is stuff that you can do that's hands-on. Things that you're not just listening to someone or reading something, but doing something. So coming to events like this, when you have a chance to actually go observing. I can tell you, these pictures that I can get from Hubble, they're spectacular, and they're higher resolution and in greater detail than anything you can ever see with a telescope on Earth with your eye. But there's something magical about actually seeing it with your own eyes. So for me, I think that if I would say what was the thing that I value the most about when I was younger, in terms of putting me on the path, it's being creative, but not just sitting and thinking, but actually doing stuff, building things, learning electronics and soldering together projects, doing little chemistry experiments, stuff like that is, I think, totally indispensable. And in terms of astronomy, the kind of things you can do there is actually going out hunting through the sky, finding things, learning about how to orient yourself. And today, one of the really important tools for every kind of science is knowing how to use a computer. So learning how to program, writing games, writing your own little games is a great way to learn how to program. Yeah, thank you.
Okay. I got two questions.
Okay.
to ask you about the crisis in cosmology,
Mm-hmm.
and specifically about type 1a supernova. You measure the expansion rate of the universe, looking at type 1a supernova, you come up with a Hubble parameter, about 73 kilometers per second per megaparsec.
And if I go back to this tells you it should be
67.
68,
67. The error bars don't overlap.
Yep.
Couldn't I argue that the discrepancy is a result of type 1a supernova that don't all calibrate at exactly the same brightness because of, you got a white dwarf and you got a companion star that are causing an explosion, that's not necessarily going to be the exact standard candle every time, and there could also be dust absorption, or is there something else going on? How do you rule that out as the discrepancy?
Good question. So, I think the question is, how do we, okay, there's this problem where if we measure the expansion rate from looking at the cosmic microwave background radiation, it says it's a little bit slower than if we measure it from looking at stuff in the universe that's closer to us than that cosmic microwave background radiation and measuring how far back or how fast it's moving away from us. So the way we measure distances is mostly at large distances with these standard candles. So things that we know what their brightness should be, and we measure what their brightness appears to be, and that tells us how far away they are. So the best one is this type 1a supernova. These are ones that can go very far back. Why are they the best is the question. One reason is that they're already very bright. If something is a standard candle, but it's not very bright, you're only going to be able to see it when it's close to you. Not very useful for measuring big distances. Supernovae are tremendously bright. But why don't we use, so type 1a supernovae are caused by the deaths of white dwarf stars. Stars that are kind of already dead, dying again. Core collapse supernova, like I think the Crab Nebula is a core collapse remnant. These ones are massive stars reaching the end of their lives. These are typically brighter than type 1As. Why don't we use these? Well, the reason we don't use these is because they're all different brightnesses. We have no way of really pinning down exactly how bright one of these actually is. So why are type 1As the same brightness? Well, the thing that causes them to go off is a white dwarf star is a star that's no longer held up by nuclear fusion, reactions in its core heating it up. It's actually held up by quantum mechanics. A white dwarf star is electron degenerate, which means the electrons in that star are packed so tightly that the Pauli exclusion principle, a feature of quantum mechanics that says that two particles can't occupy the same space if they're a fermion. Don't ask me to go into detail about that because we'll be here all night. Because those things can't occupy the same state, they're packed so close together that to compress the white dwarf any further would violate that principle. That's what holds them up, is electron degeneracy pressure. Well, what happens if you pour more material onto them? Well, they shouldn't get any denser. There's a way out of this. What if you just get rid of those electrons? If the electrons are the thing holding you up, if you get rid of them, you can collapse down. And so if a white dwarf star gets heavy enough, it becomes energetically favorable for those electrons to become captured by neutrons and turn into protons. It causes a kind of reaction that only occurs, what's called a phase change, that only occurs in really high pressure. This is really good timing. I'm just teaching phase changes in my statistical mechanics class. There's phase changes like this happen on Earth. So if you take water and you try to boil it at room temperature, or at sea level, it boils at 100 degrees. If you go up to Mount Everest, it'll boil at 70 degrees. If you bring it into space where the pressure is really, really low, it'll boil at room temperature right in front of your eyes. So stuff can change phase based on the pressure. And in neutron stars, electrons and neutrons can change phase into protons if the pressure is high enough. The problem is that releases a lot of energy. It's exothermic. So we can calculate from first principles, just using quantum theory, how big a star has to be before it will convert its electrons and neutrons into protons. And that happens at about 1.4 times the mass of the sun. So 40% heavier than the mass of the sun, one of these white dwarfs will go through this phase change. And the amount of energy that's released by that phase change is enough to unbind the star. So it explodes, leaving nothing behind. Because it always occurs at exactly the same mass, though, it always has the same amount of energy. And so with some detailed corrections for things like rotation and things like this, we have a good idea that white dwarfs should have a certain brightness everywhere. Now, there's lots of stuff that can confuse this, of course. What if you're picking up brightness from a companion star? What if that light's coming through dust? We think that if everything was perfect, if there was no interference in your observations, they should have the same brightness, but life's never that easy. Well, there's a couple of ways to get around this. One is if you're seeing light from the companion star, it's going to be at a much lower temperature than light from the white dwarf. White dwarfs have surface temperatures about 30,000 degrees. The brightest star has a surface temperature of about 10 to 15,000 degrees. The other thing is if it's dust, if say some of that dust is getting blocked, dust never absorbs all colors of light equally. And so what you would see is a tweak in the shape of the spectrum because of that dust. Cosmologists have been working on this, trying to figure out, are cosmologies wrong, or is it systematics in the observations? I think at this point we've pretty much ruled out systematics in the observations. I'm really of the opinion that the Hubble crisis, as it's called, or the crisis in cosmology, the gentler term is the Hubble tension. That's what we see when we're not trying to scare the crap out of each other. I would bet a small amount of money that it's probably going to persist, and it's going to require us to modify dark energy. Again, I would maybe bet a couple of dollars on that. But one of the things that could help us out is getting better and better observations of the first couple 100 million years of the universe, as well as getting more and more precise measurements of things like the spectrum of how many massive versus less mass galaxies there are, and coming up with other ways to do this. So the issue is we have method one. I got two rulers. One says that the chocolate bar you gave me is 3 inches long, and the other says it's 2 inches long. I mean, one of them is wrong, or both of them is wrong. So the best thing I can do is find some other rulers. And so we're trying to find other rulers. The problem is most of them are harder to use. So doing precision cosmology with galaxies is very hard because unlike a type 1a supernova, I can't tell you from first principles much of anything about galaxies. We have to go to simulations, which is why people like us exist, but our simulations are very uncertain. So hopefully we can tamp down some of that uncertainty, and we can start coming up with other ways of measuring the Hubble constant. And if it turns out we get 4 more ways of measuring it and all of them agree with Planck, then yeah, it probably means that we didn't understand some systematics with the type 1a. But if they all agree with type 1a's, then that means cosmology has to be modified. Yeah.
I have another question from
okay.
online observers. Would electrons and protons form neutrons instead of electrons and neutrons forming protons?
Oh, yeah, I misspoke. Electrons and protons form neutrons. It's inverse beta decay. Yeah, you're right, I misspoke. So you have a positive and a negative charge that cancel to a neutral. Normally, in room temperature, or anything other than the degenerate cores of the white dwarf, a neutron by itself is unstable, and it will decay into a proton and an electron.
Right.
Raise the pressure high enough, it goes in the opposite direction. Again, a cup of water at room temperature is liquid. Raise the pressure in here high enough, it'll freeze, even at like 80 degrees Fahrenheit.
Okay, wrapping up, last thing.
Okay.
Not yet.
Not yet.
I'm not done with you yet.
Oh, no.
This is kind of part question, part sales pitch. I know you're teaching a class this semester on statistical mechanics.
Yeah.
We've talked before and you're not having a very good time. Since you couldn't talk enough and you were really excited about this class, you want to just kind of share your experience teaching this class and why this is such a great class to teach and what you're experiencing teaching statistical mechanics?
Oh, I mean, I'm having a ton of fun teaching stat. StatMech was my favorite course in undergrad physics because it blows your mind that some of the laws of physics are actually just a consequence of counting. Things like the laws of thermodynamics. Why does heat flow from a hot object to a cold object? Counting. Counting. It's just counting. All it is, the idea about entropy in the universe, the idea that the entropy of the universe increases, sounds very mystical, sounds very, I don't know, esoteric, must require some really, really hard physics to understand. Well, the entropy is just a measure of all of the different ways in which things can be. And so if there's only a handful of ways for something to be in this state, but there's millions and millions more, and really millions is a tiny number in statistical mechanics, and you're just flipping coins into, well, this thing has 10 possible ways, this thing has a million possible ways, and you're just flipping at random. Well, there's a lot more ways that you can land in the million possible ways than the 10 possible ways. And that ultimately is all that sets up things like equilibrium, the flow of heat, or diffusion, is all comes down to counting, permutations, how many different ways in which things can be. And what's truly remarkable is that's actually the same theoretical framework for talking about information. If you ask me how much information is being conveyed in these words, I tell you the same mathematical function for the amount of word or information in that word is used to calculate the amount of entropy in a physical system. So StatMech is cool because it connects something that would be true in every universe, counting, basic math, stuff like that, to something that is true in our universe, the laws of physics, thermodynamics. So it's the only thing where you can't really say, well, what if it was different? Because I can't argue, or I can't reason about a universe where logic doesn't work.
I think some people's words increase entropy more than others.
Yeah, but it's great fun. It's great fun. One of the great joys of teaching is you learn yourself far more than you thought you did. You think, oh, I knew this. I've got my PhD. It's like, oh no, you don't know it until you've taught it. Yeah.
Fun class to take.
Thank you.
Give them a hand, everybody.